Hi gang, so projectile motion is the topic of this video. Projectile motion is like it sounds. That is projectile motion. That is projectile motion. When something is given an initial force and then it just starts to act, and then it's not acted upon again. Gravity takes it into gravity takes it from there on. That's projectile motion. It becomes a projectile at that point. Given an initial force, and then gravity just does the rest. That's projectile motion. So we're going to talk about two types of projectile motion today. The first type is if you are deployed from the lander. Basically, it's just what I did. That is projectile motion. If the lander lands and you deploy from the lander, or if the lander is even descending, you can be deployed from the lander as well. It works the same way. And we're also going to be talking about if you're deployed from the orbiter, what happens as you go toward the ground. And if you want to target a certain area on the surface, if you're deployed from the orbiter, how do you target a certain area on the orbiter, or from the orbiter? Some of you want to target certain areas on the ground that you want to hit. So how do you do that? So the first one we'll go over is just, if you land with the lander, projectile motion. How does that work? So you guys should have studied this in physics class, so this should be review. But basically, projectile motion, everything it's all parabolic. It's not circular, it's parabolic motion. So excuse my bad drawing, but that's projectile motion. You just, let's see if I can throw this. Yep, that kind of traces that. Traces that parabola, right? So if you give something an initial velocity in this direction, it's going to have components in the x and the y direction. I'm going to set up my coordinate system. So this is positive x, and this is positive y, the standard coordinate system. So this will be vy, and this will be vx, and this will just be v, okay? And then you'll have an angle right here, theta. That's our angle. So how do you find out how far downstream did it go? What's the distance that it traveled? D, from here to here. What's that D? Okay, because if you want to get to a certain distance, how do you find that distance? You want to get 10 meters away from the lander. You want to get 100 meters away from the lander. How do you get that distance away? And then if this velocity is given to you from the muzzle, then go watch the muzzle velocity video to determine how to find that velocity based on pressure. But we won't talk about that in here. But if this velocity comes from the high pressure gas, you got to go watch the muzzle velocity video. Basically, it's all about time of flight. And one certain key things to remember: your velocity in the x direction never changes. Once you're given an x velocity, your velocity in the x direction stays the same the entire time. Your velocity in the y direction is never constant, okay? So x direction never changes, it's always constant. Y direction is never constant, it's always changing, okay? So because y is under the influence of gravity. We've got gravity acting down on us, right? Gravity is the force that's pulling down on us. So write out our lovely equations for projectile motion. V final squared equals V initial squared plus 2AD. V final equals V initial plus AT. That's time. D equals VI T plus 1/2 AT squared. And then distance, D equals velocity times time. These are the four basic equations for projectile motion. They all assume constant, constant forces, constant acceleration, stuff like that. So those are some of our assumptions. Constant acceleration is one of the main ones because A is a constant value in all these. So for the first one, if we are launched and we end up downstream, how do we find our distance? So we're launched and we're given an x component and a y component of the velocity. You can find that through trig. I'll trust you guys can do that. Okay, so let's just solve in the y direction. Y direction. What do we got going on? Let me get my cheat sheet out. In the y direction, we can use this equation. V final in the y direction equals V initial in the y direction plus AT. So just remember, you can take your x and your y, they can be separate. So your y basically, So basically the y just goes up and comes back down. That's all the y velocity does. It goes up and comes back down. Now what happens is the x velocity comes in, and that's the reason it goes downstream, is your x velocity pushes downstream, but the y velocity just goes up and comes back down. I gotta go find my marker now. So that is, so you can separate the two velocities. Y just goes up and back down. So for the purposes of finding our time of flight, we just say the y velocity goes up and then back down. And we'll make this, let's make this big D and make this little d. So we're looking for little d there. What is our y velocity at the very top here? At the very top of our at the very top of this flight, what's the y velocity? What's the y velocity when it gets to the top? It's 0. For a very, very brief moment in time, it stops and then comes back down. It goes, stop, come back down. Stop, come back down. So our final velocity in the y direction is 0, okay? That's what it is up here. And this is just for half the trip, okay? So v initial in the y direction is whatever we shot it off with, whatever we gave it in the initial direction, that's our v initial. So v initial minus v initial y equals acceleration times time. So if you're looking for your time of flight, for half of your time of flight, it's minus v initial. That just means that it's slowing down, divided by your a. And a in this case is going to be the gravity on whatever planet you're on. If it's Earth, it's 9.81 meters per second squared. So that is how you find the time of flight that it takes you to go from the surface to the top. And the time it takes to get from here back down is the same time. So this is 1/2 of the time of flight. And so time of flight equals 2t, okay? That's how you find your time of flight. So it goes up and then comes back down. So what I just saw for was the up portion, then it comes back down at the same time. So that gives us time of flight. The time that it's in the air is time of flight. And so how far downstream did it go while it was in the air? That's downstream is the x direction. So x direction. X direction's easy because the velocity is constant in the x direction. So it's just distance equals velocity times time. And in our case, we're going to change that to time of flight because I'm using different variables here. So velocity times time of flight. So the distance that it goes in the x direction, the distance downstream, equals the velocity in the x direction times the time of flight. And time of flight is just 2 times v initial in the y direction. So dx equals vx times 2 times v initial in the y direction over a, if you want to get real crazy with it. So that's how you solve for the downstream distance. So that's going to be, sorry, that's a big D. Oh my goodness, Matt. So that's what that is. So big D is basically it's the time of flight that you have, the things in the air, the things flying, times the velocity in the x direction. And the time of flight just happens to be 2 times this value right there. So there you have it. That's how you calculate time of flight. And if you are, if the lander has not landed yet, if you're deploying from the lander while it's descending, same thing applies. You just keep this going. Okay? So your time of flight will not be the same going up and coming back down. Okay? But you can calculate this simply by saying that you know where you know the time of flight, you know your distance. And you can use this equation here to calculate time of flight. So you know your distance, and then you know your initial velocity in the y direction when you get to the top here is going to be 0, and then you're going to be accelerating downward. And if you get shot off just in the straight direction from the lander, then actually it becomes the same problem as if you were shot off from the orbiter, which is what we're going to do right now. So if you're shot off from the orbiter, or if you're shot off from the lander, while the lander is descending and you're shot off straight out in the x direction, you're not given any y direction or not given any y velocity at all, what happens to you? So if you're here and you have an initial velocity in the x direction, and again, that could be because you are being deployed from the orbiter or because you're being deployed from the lander just in the x direction, what happens to you? Basically, it's in physics, if you've done the cliff problem, it's the cliff problem in physics. So it'll amount to this, essentially. There. That's the cliff problem. Does it look familiar? Basically, it's like a cliff. That's what's called the cliff problem. And so, how far downstream do you go? D. How far downstream do you go? So, where we calculate that is let me get my cheat sheet out. So, V final squared equals V initial squared plus 2AD, where this is this D, right? So that's that distance that you're falling. Your initial velocity, this is only in the y direction, okay? So this is y direction only. Your velocity in the y direction when you start off is 0. You have no y velocity at all. You have x velocity, then you start to have y velocity. So initial velocity in the y direction is 0. Your final velocity we don't know, but we do know d, the distance you're falling, and we know a, right? We sort of know a. So v final squared equals 2AD. So you solve for, if you want to use gravity, local gravity, that's fine. If you're deploying from the lander, you can just say, okay, the gravity on this planet is such and such, and that's going to tell us our final velocity. That's going to tell us our final velocity at the bottom. The d equals VIT plus 1/2 AT squared. That's going to tell you the time that it takes to fall. So again, in the y direction, initial velocity is 0. So we know our d that we're falling, right? If we're falling like 100 meters or 300 meters or whatever, we know that. So equals 1/2 AT squared. And you solve for t to find the time that it takes you to fall that. So this is going to tell you your time of flight. Now here again, A can be local gravity. And I'll talk about some ways to make that a little more advanced if you want. So local gravity. So again, this is, even if you're falling off of the orbiter, okay? This is a lot of x velocity if you're falling off the orbiter. But still, as long as you don't have an initial y velocity, you're okay. If you do have initial y velocity, if you're on the orbiter and the orbiter kicks you down, then this is just not 0. And you have to solve this quadratic equation. It's not that hard. You can solve it. But it's a little more difficult. It's easier if you don't have any y velocity in the beginning. So what that ends up with is, so this gives you your t equals time of flight. Okay? And then again, just like with the last one, x velocity never changes. So whatever velocity you have here when you're leaving is the same x velocity you're going to have the entire trip down. So in the x direction, big D, big distance downstream equals velocity in the x direction is time or time of flight. And then, so that tells you how far, that's going to give you your distance downstream based on your initial velocity in the x direction and the time that it takes you to fall, okay? Now, if you're targeting a certain area, if you say, I want to hit this, okay? Then what that tells you is that if it takes you 100 seconds to fall and then you fall, and then you go, and then you end up going, I don't know, 1,000 kilometers in that 100 seconds or something like that. That means in order to hit this spot, you have to release way back down there by 1,000 kilometers, right? Which might be, you know, halfway around the planet or something. But it's still the same thing, right? Okay? It's just knowing how far you go after you've been dropped based on the time it takes you to fall, okay? Again, X and Y velocities, you can rip them apart. The thing that ties them together is time of flight. The time that you are in the air or time that you are flying is the thing that keeps X and Y velocity together. So just look for your time of flight and it'll tell you everything. Now, I talked about using local gravity. If you're on the lander and you're descending and you pop off the lander, using local gravity is fine. If you're on the orbiter and you pop off of the orbiter, you're going to be pretty high, maybe 200 or 300 or I don't know, 100 kilometers above the surface of the planet. Gravity is not going to be that, it's not going to be sea level gravity at that point, right? Gravity gets less and less as you go higher and higher. So how do we solve that? If you want to, you can assume local gravity. Just make sure that you specify that you say that I held gravity constant the entire way down. Otherwise, let me just erase this real quick. We talked about in the orbital mechanics and the orbital velocity, Fg, force of gravity, the Newton's gravity, is big G, big M, little m over r squared, right? Now, that still equals, because not mg, it equals ma. It still equals ma, even if because you're still a mass and you're accelerating. Newton's law still works out there. So what you do is you solve for acceleration to plug it into this equation, okay? So your masses cancel because gravity does not care how much you weigh. Gravity pulls you down no matter what. A equals big G, big M over r squared. So what you can do is you can calculate the acceleration for different intervals as you start to fall. Like if you fall from about 200 kilometers altitude, you can calculate velocity, or calculate acceleration at, and remember, this is r, this is not altitude, so you gotta use the r of you gotta use the radius of the planet plus the altitude, okay? Don't forget that. This is r, not altitude. But, so what you're gonna see is that, we've showed you this already, is that compared to the radius of the planet, the altitude's not that much. So this won't change that much. It'll change a little bit, but it won't change that much. So that's why I'm saying you can use local gravity at the surface if you want to, for the entire trip down if you want to. So, but you can calculate if you say, let's say we deploy at 200 kilometers, you can calculate the value for the value for gravity at 200 kilometers. You can calculate it at 150. You can calculate it at 100. 50. You can just and then stitch those together, and then you'll end up with time of flights from this one to this one, this one to this one, and this one to this one. So you'll have T1, T2, T3, and then obviously T4, because you haven't hit the ground yet. But for the last 50, you can just use the value of local gravity. Just use G for that. But so you can stitch those together, and those will become your time of flight, and that's what you plug in. Your x velocity still does not change. X does not change unless something acts on x, okay? Unless something gets in your way or you have drag or something. X does not change. X velocity does not change. So that's how you calculate time of flight. If you want to vary, if you want to say, we want to be a little bit more accurate than just saying we're going to use sea level gravity, sea level, whatever the gravity at the surface is, surface gravity. We don't want to use surface gravity. We want to be a little bit more accurate with that. What you'll see is the time of flight, it takes a little bit longer to fall, okay? You can set it up in a spreadsheet and do every meter if you want to in a spreadsheet. It's just drag it down. It's a calculus problem. You can set it up as a calculus problem if you want to and have it change on its own. So that's how this works. So so again, to target something downstream, if you want to hit a certain target on the surface, calculate how long it takes you to fall, just using x direction. How long does it take you to fall? Use this equation, d equals vit plus 1/2 at squared. If your initial velocity in the x and the y direction is 0, then this falls away and you're just solving for this part. But just use the y direction to calculate time of flight, and then use that time of flight, that time from the y direction, plug it into your x velocity, and get your distance that you went downstream in the x direction. And that tells you how far upstream you have to release to hit that point. Does that make sense? It's not that difficult. It's not hard. It can get confusing because you've got y velocity and x velocity, and the thing that ties them together is the time of flight, the time that it takes to fly. Otherwise, they're independent of one another. Y velocity is this, x velocity is this. X never changes unless something gets in its way or some force acts on it. So it's constant the whole time, and y is never constant. It changes the whole time. So that's projectile motion in a very, very quick nutshell. I did this very quickly. I wanted to get the video done fast. There's a great Wikipedia page about it. There's some stuff on the downloads page about this that follows this. If you have any other questions, contact me. You should have studied this in physics. This is a little bit more advanced. This is a big cliff problem because your cliffs are going to be in the order of, could be 200 kilometers tall. But if you have any issues, email me or PJ or your UAH project manager, and we'll help you out. Thanks a lot. Bye-bye.